Okay, so we will begin the review now. Data representation. Of course, you are aware that we have like what we call the binary numbers. We'll see like how we can translate between binary and decimal. We'll see how can we do binary or review. I know that you already know this information, and I hope that you still remember. Integer storage sizes, hexadecimal integers, translating between decimal and hexadecimal, hexadecimal subtraction, signed integers, binary subtraction, and character storage. With this some basic definition, I'm assuming that you will be familiar with this. 1 millisecond is 10 to the power negative 3, 1 picosecond is 10 to the power negative 12, and so on and so forth. Also, one very important stuff here, that the kilobyte is not 1000 byte. It's 2 to the power of 10 bytes, which is 1024 bytes. So if I'm telling you that this is kilobyte, it is 1024 bytes. If it is mega, it is 2 to the power of 20, and so on and so forth. If it is gig, it is 2 to the power of 30, and so on. So I'm expecting also that you will be aware of this. And this is not the same as kilohertz, because kilohertz is basically 1000. And this guy, it is not 1000. It is 1024. Okay? Okay, binary numbers. Of course, from the 270, you know that we have either 0 or 1. And if I have a number like that from bit 0 to bit 15, I will call this is most significant bit, and this is will be least significant bit. With this binary number, so if I have here 1 or 0, which means that each bit is either 0 or 1, I would like to comment that the issue that we are saying that this is binary number, so this does mean that we are saying that we are working with something called a base of 2. A base of 2. In our normal counting, we are working with a base of 10. When we went to the kindergarten, first grade, second grade, all of this, we played with base 10. And that's why it's much easier for us to understand base 10. But unfortunately, the computer will not understand in that sense. It would be very, very difficult. The brain of the computer will not be able to differentiate between numbers if they have a base of 10. Instead, designers thought about that a lot, and they have designed it in a way that, okay, let's go with binary. Why binary? Because I am telling the CPU either to understand if it is 0 or 1, and this will be much easier. If you think like with the hardware, if you would like to implement something like that, it's much easier for our system that we will design either to understand that this is 0 or 5 volt as an example, or 5 volt or 10 volt. I have just 2 choices. But can you imagine if I'm giving like 10 choices? Yes, as an example, from 0 to 10 volt. And if it is 0, this is this. If it is 1, if it is 2, how about 1.23? How about 1 point? Is it 1 or 2? Or is it 2 or 3? And so on. We'll get like to a hassle. And that's why they have designed it just like with 2 options. Either 0 or 1. And this one is logic, meaning that it doesn't have to be physically 1 volt. It can be 5 volt, it can be 10 volt, it can be 20 volt. I have just 2 options. Either right or left. Yes? And logically, we will say like the right as an example is 0 and the left is 1. And if I am counting with bases, so I have always to have the power of that base. In another sense, when we had earlier in first grade any number, so if I'm telling you that you have this number, and I'm asking you to read. Of course, first grade, you will not be able to say like this is 1,000, yes? Assuming that you are in the second or third. You'll say like, hey, this is 1,000. What exactly happened in your brain? That you know that you are counting with a base of 10, and that's why this is, you call it the unit, this is, you call it the tenths, this is, you call it the hundredths, and this is, you call it the thousands, and your mind or your processor inside your brain say like, hey, this is 0 at this location, 0 at this location, 0 at this location, so it doesn't have any value in the units, doesn't have any values in the tens, it doesn't have any values in the hundreds, and it does have one value, which is 1 in the thousand, and that's why I will interpret that as 1,000. When you become like a little bit bigger, we told you like, hey, units means that you have the base of 10 to the power of 0. So this location is a base of 10 to the power of 0. So that particular location is holding that particular power. In another sense, if I have 1 at this location, which is here, it will not be interpreted as 1 at this location. In another sense, you can think of this like we are both like two people, yes? But I am in another base, that I am the professor. You are the student. So even if we are two persons, yes, but we don't have the same power, or we don't have the same base. Correct? So with this has a base of 10 to the power 0. This 10 to the power 1, 10 to the power 2, 10 to the power 3. And what you are doing in your mind exactly, if we would like to break down in order to read that number, you are saying 10 to the power 0 multiplied by the number that is here, 0, plus this power, 10 to the power 1 multiplied by the value here, which is 0, plus this guy, which has the power of 10 to the square, multiplied by that number, which is 0, plus 10 to the power 3 multiplied by 1, which is the number that is here. Correct? This is exactly what we are doing with binary, or with another base. It can be base 2, or it can be base 5, or it can be base x, or it can be base apple, it can be base orange, whatever the base is. It will be apple to the power of 0, plus apple to the power of 1, and so on and so forth. It will be x to the power of 0, yes, multiplied by whatever the value, plus x to the, and so on and so forth. Agree? So if I were to ask you, like, please read these as a binary, so this will be 2 to the power of 0, this is 2 to the power of 1, have the power of 2 to the power of 2, this is 2 to the power of 3. And again, I will multiply 2 to the power of 0 multiplied by this, which is equal to 0, plus 2 to the power of 1 multiplied by this is 0, plus 2 to the power of 2 multiplied by this is 0, plus 2 to the power of 3 multiplied by 1 is 8. So this will be read as 1000 if it is decimal. This will be read as 8 if it is binary. Correct? Okay. So one more thing I would like to highlight. If I'm telling you that we have a base 2, again, would like to emphasize that I have two options. And we claim that these two options is either 0 or 1. If I'm telling you that we are working with a base of 10, so this means that I know in advance that I have how many options? 10. Which we learned as from 0 all the way till 9. And with these options, I can create any numbers. Correct? So with the binaries, I will only have zeros and ones. So if I'm giving you like 2, 1, 2, and I'm asking you to read this as a binary, you say like, hey, I don't know what is this 2 because I have only 2 options. Now you are giving like a third option. I can't. Yes? And that's why with the decimal, I can give you like 999, and you can read that because 9 is one of the options. So it will be 999 or 989 or whatever the numbers are, correct? If I'm telling you that you have a base of 8, so you know or you expect that you will have 8 options. Correct? If I'm telling you that, as an example, we are working with hexadecimal, so you know that you expect that the base is 16, so you have 16 options. 16 different options. And that's why in the hexadecimal, when we go from 0 all the way till 9, we need something afterwards because we have 16. And we have learned with our decimal system that we have only 9 options. Correct? But we need 16. How we can solve that issue? People say like, hey, let's define the 10th, 11th, 12th, all the way till the 15th option. And let's say that the 10th will be A, then the following will be B, then the following will be C, and so on and so forth. But it can be anything, correct? I might have like another base in the quiz or in the exam, and I can give you like what will be the representation, and I ask you all of these general questions. The concept is exactly the same. That's why when you solve all of these things, you have to understand the concept. If you do understand the concepts, anything else will be just like easy and following just like the same steps. Okay? So I'm just like trying to give you like all of this introduction before we go further into the explanations or into the review. So this is just like shows you some of the decimal values. I'm not expecting that you remember this, but this is just for your information. Again, if you have like something with the decimal or the binary, of which is decimal 9, you will say like, hey, this is 1 multiplied by its power, which is, sorry, 2 of 0. This is 0, this is 0, so I don't care. This guy has the power of 2 to 3. I multiply by that, others are 0. If you do 1 multiplied by 2 to the power of 3 plus 1 multiplied to 2 of 0, your brain, according to your brain, will understand that this is 9. Which gives you another indication that if your brain can see the 9, unfortunately the CPU, I have to write it for the CPU like that in order to be understood as the same as the interpretation of 9 in your brain. So we have 2 different coding schemes, your brain and the CPU brain. The CPU brain, if I would like to tell the CPU brain 9, unfortunately I have to write it that way, 0, 0, 0, 0, 1, 0, 0, 1. In our brain, it's just like 9. Okay. If I would like to translate unsigned decimal to a binary, in another sense, I'm giving you that you have 37 in your mind. How you can write this in binary? What you will usually do is just divide by the base that you are translating to. So if you would like to translate to binary, you have to divide by 2. If this is hex, you have to divide by 16. If this is oct, you have to divide by 8, and so on and so forth. And then you will get the quotient and the remainder. 37 divided by 2 is 18. The remainder is 1. 18 divided by 2 is 9. The remainder is 0, and so on and so forth until you get all of the numbers. How you will transfer this? You have to know that this guy will be the most significant bit. This guy will be the least significant bit. As you can see from here, this one is here. This 0 is this. This 0 is this. This one is this. This 0 is that. That one is this guy. If you have something like that in the quiz and you write it the other way around, unfortunately you will not get the grade for that particular, because you don't understand how you do that. Even if you did this, but the interpretation at the end is wrong number. So you have to be aware with this translation. So in the quiz or in the exam, either you will write it to me like that way, or you just write it that this is M, this is L, and this is M, or MSB, LSB, and so on and so forth. Binary addition, I'm expecting that all of you are aware of that. 0 plus 1 is 1. 0 plus 1 is 1. 1 plus 1 is basically 2, which is 0, 1. Correct? Yes, 1 plus 1 is basically 0, 1. And 0, 1 is what? It's basically 2. In our brain, it's 2. Why? Because this guy had the power of 2 to the 0. This guy is 2 to the 1. We multiply 2 to the 0 multiplied by 0 plus 2 to the 1 multiplied by 1. This will be equal to 2. So basically 0, 1. And that's why we have here the 0. And we carry 1. 1 plus all of these 0 is 1, and so on and so forth. I think it's easy for you to catch that. So I'm going fast because, again, this is a review. I'm not expecting that this is new material. With these hexadecimal integers, so they are like 4 binary bits, and this will be the decimal, this will be the hex. If you will go like from the 0 all the way, as I mentioned, till 9, because we have 9 options. After 9, how I can represent the one after that? In our binary, in our decimal, I can use 2 of the options to create the 10th, yes? And 2 of the options is 1 and 0. I have these options. Yes? And then I am creating the 10. But with the 16th, how I can create the 10th option? I don't know. That's why they are just like agreed that we will call it A. Then, how about the next one, the 11th? I know that I can take 2 of these decimal options, which is 1 and 1, and I can say that this is 11. But unfortunately, with the hexadecimal, I don't know. That's why we call it B, and then C, D, E, and the last one is F, which is basically 15, and is just corresponding to all ones. My question is, why the hexadecimal is base 16? Translating binary to hexadecimal. So this hexadecimal, as we mentioned, we have like 4 binary bits. So if you have all of these binary, and I would like you, or I'm asking you to translate to hexadecimal, so it's basically you are getting, or you are taking just like each 4 of these and interpret it as a number of one of the options that you have for the 16 base. Since the first one is 0, 0, 1, 0, this is, if you do that, it will be, as an example, 4. If you do this, it will be 9. If you do this, it will be in decimal 10, but we don't have 10. Yes, we have A, and so on and so forth. So this means that with the hexadecimal, I can go all the way till 16 different options. And from the 17th, what I will do? Combine any of the previous options to create the number 17. Yes? How I will define 18? I will use 2 of the other, or 3, whatever the options that I had, to combine together to create number 18, and so on. It's exactly as we had with the decimal. After the 9, I will begin to take like 2 of the options, as an example, to represent the 10th. Yes, if I will go to 100, I will take 3 of the options to represent the 100, and so on and so forth. Got it? So converting hexadecimal to decimal, I think like all of you can do that. It's easy. So if you have the hex is this 1, 2, 3, 4. Of course, with my eye, I have to know that this has the base of 16. And since it has the base of 16, this 4 is not 4 multiplied by 10 to the power 0. It is 4 multiplied by the base to the power 0, which is 16 to the power 0. This guy is 3, but it doesn't hold the power that I always have in my mind, which is 30. It is not 3 multiplied by 10 to the power 1. It is 3 multiplied by the new base, which is 16 to the power 1. If I am telling you that 1, 2, 3, 4, but we have base x, so it will be 3 multiplied by that base to the power of the location. Correct? So you can do this yourself. It is exactly the same concept. Again, it is powers of 16, and we already explained why that. This is just like for your information. I'm not expecting that you remember any of these. Converting decimal to hexadecimal is exactly with the same exact scenario. Instead of dividing by the base 2, you are dividing by the new base, which is 16, and then you'll get the quotient and the remainder, and at the end you will combine the remainders, and again this will be the least, this will be the most. Correct? Hexadecimal addition, and please concentrate here. A plus B is what? It's basically A is in our minds in decimal is 10, yes? And B in our mind is 11. So 10 plus 11 is 21. But I can't write 21 because this 21 is in the base of the decimal. So I have to transfer this 21 to the hex. Correct? And this is what we will do. So it is 21. Transfer to the hex is 16. You will get the remainder 5 and then the carry 1. So it's basically 5. And then you carry the 1. 1 plus 6 is 7. 7 plus 4 is? Yes? So it is B. Because I can say like 11, because I have to see like what is the corresponding 11 in that hex, and it is B. Agree? You can do the others yourself. How about the subtraction? Same exactly concept as we do that subtraction in the decimal. It's exactly the same concept. That we have 5 minus 7. Unfortunately, 5 is less than 7, can't be. Borrow 1. Do you remember this rule? 5 minus 7 can't be, borrow 1. But when you borrow a 1 from the left side, you are borrowing with its base. Correct? So when we have that, when we borrow the 1 from the left, it's actually with the base of 10 to the power 1. So in this case, if you borrow 1, you will borrow 1 with the base. Yes? And the base is 16 to the power of 1. Correct? And in this case, it will be 16 plus whatever the number that you have here, which is 5. Again, it is now 21. 21 minus 7 is? Correct? And this means that this will be as a hexadecimal representation as E. Correct? And since that you already borrow 1 from this 7, so it is 6. 6 minus 4 is 2. And that's why we have the 2. Clear? Yes, and the next one you can do it yourself. You can just like check this. If you have the address of that, the address of the next variable will be this. How many bytes are used by var1? You can do it yourself. Also, we have what we call the signed integers. With the signed integers, we said like, or we agreed together that we will have what we called a sign bit, and it will be the last bit to the left, which will be the most significant bit, and this is basically will be 1. If I would like to represent a negative number, and it will be 0 if I would like to represent a positive number. So if the highest digit of a hexadecimal integer is greater than 7, the value in that case is negative. Why? Because basically if it is greater than 7, so 7 means that 1, 1, 1. Yes? If it is greater than 7, so I would like to write something in this, yes, location, which would probably be 1. Yes, so if I would like to go to what we call it 8, it will be what? 1, 0, 0, 0. But unfortunately, that location is for sign bit. And since it is 1, and we said like 1 is negative, so this is a representation of a negative number. 9, 10, all of this, I will have the 1 at this location, and it does mean that it is a negative number. If I will represent this as a sign. And that's why it is very important to agree for a certain way to read. Meaning that I have to tell you in advance that these numbers, read it with this format. And if we agree together to that same format, so we both can read the same number. And that's happened when also you work with the computer. If you're telling like it is unsigned, the computer will read it that way. If you told like this is signed, the computer will read it in another way. Correct? With this signed integer representation, as you can see, 1 plus 0 is 1, 1 plus 1 is 2, which is 0, carry 1, and so on and so forth. And at the end, you will have 1 plus 1, it's 0, and then carry 1. Oops, I don't have enough place to carry this number, and unfortunately, when you do that, you will find that 107 plus 46 is 25. And this happened because of something called overflow. Yes, it's an overflow. Why? Because unfortunately, I don't know what to do. I have not been trained, or the location that I had, unfortunately, cannot carry all of the stuff that you would like to give to me. As an example, you have like a storage that can hold like for 10 boxes. I'm giving you hundreds of those. I can't. If you remember that when you was a child, kindergarten, and unfortunately at that time, you can count only from 1 to 10. Then it's like, hey, please count from 1 to 20. What they will do at that time is what? 1, 2, 3, all the way till 10, and then 1, 2, 3, yes, 4, and so on. So if you would like them to actually count 16, say like, hey, they will round out to 6 because of the overflow. Because they don't know how to represent the 16. And that's why they will begin from the very beginning, 1, 2, and then they will stop at the 6. It is an overflow. And this, by the way, is a common problem in the systems. And the designers need to take in advance all of the overflow options that may happen in the future, and choose the representations of numbers that will correspond to the lowest error. We'll go over that later on. Okay? Again, with the same, if I have like a negative number, and then try to find the sum of the negative 46 and the negative 29. In this case, because the signs are the same, all we do is add the numbers and supply the negative sign when we are done. And that's why we have here the both are this, and that's why we have the negative at this, because this minus this, it will give me another negative number. So the sign magnitude representation is easy for people to understand. Just like I'm telling you that the most significant will be 0 in positive, the most significant will be 1 in negative. But unfortunately, it requires complicated computer hardware. And another disadvantage of a sign magnitude that will allow 2 different representations for 0. As we will see, or as you may know, that I will have positive 0 and the negative 0. Because if I have that number, and I'm telling you that this is the sign bit, this location is the sign bit, and I'm telling you that you have this number, please read this and read this. Hey, this is 0. okay, and this negative 0. Correct? So I have actually two representation for exactly the same thing. Yes, I mean, it's nothing, and this is a problem. And that's why we need to basically complement the systems for numeric variable representation, and that's why we will define something called the 2's complement. And they found by having a 2's complement, they will not face that problem of having two representation for the same number. How we can do a 2's complement? If you remember, we just flip and add 1. Yes? And this basically the adding of 1 in order to avoid this problem of two representation of the same number. If I flip and add 1, this is what will be the case. You can easily follow that example. I don't have to spend time for things that is really too easy. With the binary subtraction, a minus b, since we have what we call 2's complement, so I can get a plus the 2's complement of b, correct? And this does mean that I am doing a minus b, and it will be much easier. In this case, if I have this a and this b, a minus b, I will do like a plus the 2's complement of b, which is this one. It will give me that guy. And if you were to go and do like a minus b, you will get the exactly same number. So this table just shows you whatever like the problem that I'm telling you. If you have a binary representation like that from all 4 zeros all to 4 ones, and you have the unsigned will count from 0 all the way till 15. So this is not a problem. With the signed, I have from 0 all the way till 7, and unfortunately after that I will have minus 0, which has the problem of this, and then minus 1 all the way till the end. With the 1's complement, I will have 0 all the way till 7, and then from minus 7 all the way till here, but I have again the problem of 0 and minus 0. With the 2's complement, I will have 0 all the way till 7, and here minus 8 all the way to minus 1, so I don't have the problem of two representation of 0. And you can think of this here that way, that with the 2's complement, it's basically, for the positive numbers, it's exactly as the unsigned. This and this are exactly the same. Correct? After that, this guy with the 2's complement, I will count with this most significant bit as minus 8. And that's why here I have it as minus 8. That location will be counted as minus 8. So if I have this location as minus 8, and I have here 1, so it's minus 8 plus 1. It will give you minus 7, which I have here. If you look at the next one, it's minus 8, because this location has the value of minus 8. But this location here, 1, is basically at the location of 2, has the power of 2. Correct? Because it's 1 multiplied by 2 to the power of 1. So it has the power of 2. So it will be minus 8 plus 2. It will give you 6, or minus 6, which I have here. And so on and so forth. Okay? If you were like to go to this guy, it is minus 8 plus 1 plus 2 plus 4. Yes, minus 8 plus 1 plus 2 plus 4. It will give you the minus 1. And so on and so forth. If you have 5 bits, the last one will be, yes, as the negative, and it will be 2 to the power of negative 5, so it will be that one, and so 2 to the power of negative 4, and it will be that exactly the same way of thinking. Okay? With the Boolean operations, I know that you have like the not, and, or operator procedures, and so on and so forth. This is just like to show you the symbols, but you don't have actually to remember all of these symbols. This is just like to remind you, or just when I will use it in the other truth table, you know like what exactly that symbol is. With the not means that you will have just like an inverter, yes? If this is 0, that will be 1. If this is 1, that will be 0. It's just simply an inverter. Correct? With the AND, so if we were like to have 0, 1, 0, 1, and I have 0, 0, 1, 1, and it's kind of multiplication, yes? It's approximately kind of multiplication. 0 multiplied by 0 is 0, 0 multiplied by 1 is 0, 0, and it will be only 1 if I have both paths. In another sense, I will not pass from one place to the others unless the two paths are open. That's why I'm calling you AND. You have to specify like two things. Yeah? So with this, it's easy, as I mentioned, to see it in your free time. If you have any questions, let me know. So with this guy is the multiplexer. In another sense, multiplexer, or the symbol what we usually use, is something like that. So we will have like some inputs here, and you have a control, and then you will have an output. Correct? That controller will tell either that guy will pass here, or either that guy will pass here. So you have many lanes, as an example. Then you have like a controller. Can be like the traffic light, or it can be like someone who is really controls the traffic. And that guy say like, hey, you can go, or you can stop. The other can go. Yes? It's kind of multiplexer. You can think of this that way. But again, if you think closely to that, this controller should be able to have the many different options that I have here. In another sense, if I choose to work with the base 2, so I have only two options, either 0s or 1. Okay? So I have one bit is enough. 0 means the first, 1 means the second, as an example. But if we are 4, and I'm asking you how many bits do I need here, can I use 1 bit? Unfortunately not, because I will say like the first 0, the second 1, then the third, fourth. I don't know, yes? So I have to have like not only 1 bit, I have to have some other numbers. What is exactly that number? That number should be, if I powered to 2, should be equal or greater to that number. In another sense, if they are 4, then if I have 1, 2 to the power of 1 is 2, yes? So if I have 2, so this means that I have 2 bits, 2 to the power of 2 is 4, and 4 is equal or greater than the number of lanes. So I can use 2 bits and it should be enough. I can use 3 bits and it should be more than enough. I can use 4 bits and it will be more than enough, and so on and so forth. But the minimum will be 2 bits. So that's why, in another sense, you have log to these numbers to the base of 2. So log 4 to the base of 2 will give you 2. Yes? And so on. Agree? Converting between bases, but if we have like fraction values. So one more things like to also to highlight that if we have a number like that, and I'm telling you that this is in decimal. Okay, yes, if it's decimal, we are perfect. This is 10 to the power 0, this is 10 to the power 1, this is 10 to the power 2, this is 10 to the power 3, and this is 10 to the power of negative 1. Correct? But if I am in base 2, the professor told us that I can just remove that base and write the new base, and it will be exactly the same concept. Agree? And that's why this will be 2 to, if this is binary, so this means that this will be 2 to the power of 0, this will be 2 to the power of 1, this will be 2 to the power of 2, this will be 2 to the power of 3, and this guy will be 2 to the power of negative 1. The one after will be 2 to the power of negative 2, and so on and so forth. Yes, this is fraction. Okay, and here is the question. The quantity half is exactly representable in the binary and decimal system, but it is not the case in base 3. Why? So with this one, if I am again, just for the recording, so if I have the base 2 and I have 0.1, 0.1 means it is 1 multiplied by 2 to the power of negative 1, which is basically 1/2, which is 0.5. So I can represent this is easily. If I have a decimal number, so it's basically after the point, here is 5, so it is 5 multiplied by 10 to the power of negative 1, which again is 0.5. The problem with base 3, that if I write this is 0.1 and this is base 3, this will be 1 multiplied by 1 to the power over 3, but unfortunately this is not 0.5. So if I add a 1 here, it will be plus another 1 multiplied by 1 over 3/2, yes? Which is multiplied by 3 to the negative 2, and so on and so forth. And unfortunately, again, it will not result in an exact number. So it just shows you an example with 0.47 is 4 multiplied by 10 to the power of negative 1, 7 multiplied by 10 to the power of negative 2. If I have something like that, it is 1 multiplied by 10 to the power of negative 1 plus 1 multiplied by 2 to the negative 2. If you add this, you will get the 0.75. So again, 0.75 can be an exact representation in the number or the base 2. Okay, so how to convert between bases? If I'm telling you that you have this number and you need to convert this into the binary fraction representation, how you can do that? Instead of divide in that case, you multiply. So this will be multiplied by 2 and this, and then you will take that fraction multiplied by 2 and you get that number and get the fraction multiplied by 2 and so on and so forth. You always look at this digit. And when you do this many times, as an example, if you get here 0, you have to stop and then you will take that number. But just remember that this one here, instead of the most, at this case it is the least, and this one here is the most, as you can see with this number. So the 0.8125 in the base 10, it will be basically 0.1101 in the base of 2. Then the question is, do I have to get always zeros here? Unfortunately not. So then the question is when to stop. To stop, either it will be directed by the quiz or the exam. I'm telling you, like after 3 or 4 iterations, stop. Or I will give you like certain precision. After that, I don't care. I mean, after 4 digits, I don't care. Correct? You are already close enough to the number. So now we'll go to the Verilog. Okay, so this is basically the Verilog. So if you would like to design a circuit, so assuming you would like to design that circuit, so this guy here, has AND, inverter, OR. So this is an easy circuit. that you can actually go to the one of the designers, Vivado or Quartz 2 that you took in 270 or any other software, and then you just like grab the and then grab the or and then grab the inverter, connect it together, and claim that this input has CHP and this output is F, and of course it will function correctly as it's already defined in that particular program. Correct? This is easy. If you'd like to describe it to your friend, you can say like, hey, I have like a circuit that will do that, and I'm thinking of implementing it that way, and you write the truth table, and the truth table is doing this and this and that. Correct? But the question, so I can describe it in English, yes, but unfortunately we need something to describe this design in the hardware. What will be the case if I have something like that? Yes, horrible. Spend like hours and hours. Can you imagine if you will take like any of these blocks and begin to connect them together and so on? This is, by the way, I mean, 15 plus years ago, this is what they were doing. They were doing like that. Yeah? But then, or maybe 20 years ago, but then he said like, hey, we have to define a language. It will be much, much easier and comfortable if we define a language. One of these languages that we will study in this semester is called Verilog. And with this Verilog, we should be able to define all of these circuits, but in an easier way. So I will stop here, and we'll continue in the next time. Thank you.